Welcome to the Sentinel Hub webinar. In today's and upcoming webinar, we will introduce you to the QueryPlanet project funded and supported by ESA Philab that aims at facilitating the creation of machine learning application to tackle Earth observation challenges at large scale. Sinergise had the honor to lead this consortium of leading AI experts in remote sensing, and today we will host 4 speakers. Nicolas from ESA Philab will introduce us to the activities of the organization. Julien from How company, he will talk about super resolution of Sentinel-2 time series. Benjamin from Vision Impulse, he will tell us more about creating pan-European forest and tree species maps using Sentinel-2 imagery. And Devis from Sinergise, who will talk about efficient object detection using multiple scale satellite imagery. That is pretty much it from my side, and I give the floor to Nicolas.
Thanks, Sabrina. Good afternoon, all. Thanks for joining this webinar organized by Sinergise. So here we'll be talking about QueryPlanet, meaning how to query Earth observation big data at scale for machine learning and artificial intelligence. So this project is being funded by ESA, as already mentioned by Sabrina, and more specifically supported by the Philab, which is part of the Earth Observation Program Directorate. So we are based in Israel, nearby Rome. So first of all, a few words on the Philab. So Philab explore and apply transformative technology to Earth observation. We aim to accelerate the research and develop innovation to help some of the biggest challenges that humanity actually face, together with strengthening the European competitiveness. So this range from the effect of climate change to our day-to-day life, but also improving disaster response. We try also to identify new business model in space that can deliver better product to the community. So we aim to be like a catalyst for Europe capabilities to one, identify, develop and scale EON innovation, to convey the best and the brightest guy to rapidly tackle key question. And then we aim also to invest in highly innovative and disruptive concepts. So having that in mind, here is a snapshot of what we have currently in the pipe at the Explore office level. So here we are looking at low TRL value, I mean from, let's say, from 1 to 4, 5, and then we have also the Invest office looking at more advanced TRL value. But here is a snapshot on what we do at the Explore office. So again, it's more like a role of discovering and nurturing new ideas. From the left, you can see that we develop a wide range of exploratory activities on new machine learning techniques, starting from supervised learning, self-supervised, weakly supervised, and then we are also having some activities on generative models, TinyML, on how to compress machine learning model, and so on and so forth. One aspect which is also attracting a lot of attention in the community is the capacity for super resolution, and I think we'll mention that later in this webinar. Then we explore what we call new hybrid computing paradigms, such as, for example, edge computing, neuromorphic computing, for example, using a spike neural network associated to neuromorphic cameras. We have also some ongoing partnership with CERN on quantum computing. AI at the edge is definitely a hot topic for us. You may have heard about FISAT-1. It was the first demonstrated satellites with deep learning algorithms and the VPU chips from Intel on board. It was launched in September 2020. Now we have in the pipe FISAT-2 with even better capabilities, especially being able to upload and run on board different AI algorithms. So we'll open it up to the community with an open challenges here, so please stay tuned on that. We have some nice experimentation as well last year with Trium FDL to run, for example, on board the D-Orbit carrier, an algorithm for flood detection. We prepare also some activities with Intuition One and Capilabs in Poland, and obviously many other opportunities. We try to help the community with providing them some tools, and among others, we have been supporting Sinergise with the QueryPlanet project linked to the Sentinel Hub, and you learn that you may be familiar with. So you will know more about that in this webinar, and also the following one that is planned, I think, on the 7th of April. So QueryPlanet, what is this about? You know, AI is a great tool to extract, mine, and discover, let's say, new insight on our blue planet Earth from the massive EO data provided by the so many satellites flying now. So AI can be used for so many applications, including detection, classification, and super resolution. So in the following, you will know more about building detection with now you know more about super resolution with YI and Julien. Then forest detection and classification with Vision Impulse and Benjamin, and finally about building detection and Sinergise together with Devis. So all using open source softwares applied at large scale. So I hope that you will. Well, first of all, thank you for joining this webinar, and I hope that you will enjoy it. Over to you, Sabrina and Davis. Thanks.
Thank you, Nicola. I will just take over from the last words of Nicola. So, as mentioned, QueryPlanet is mostly about four concepts. So, first, the application of AI machine learning to the Earth observation problems. The second is doing this at large scale. And the third is open sourcing, so developing and tackling compelling challenges, as mentioned by Nicola, and equally important, open sourcing things so the community can take advantage and actually we can see an uptake of AI. So we think we didn't reach, of course, the potential of exploiting AI techniques in remote sensing. So today we will hear, as mentioned, from three use cases which have been developed under QueryPlanet. So first, Julien will talk about the super resolution technology for optical sensors, focusing on Sentinel-2 time series. Benjamin then will show us how to run forest and tree species mapping using Sentinel-2 time series at the pan-European level. And lastly, I will talk to you about the multi-resolution hierarchical scheme for building detection. As mentioned, very important pillar is the sharing, so the open sourcing of what we've done. So the code based on NeoLearn, which is an open source Python package, will be released and you will find it in the NeoLearn examples GitHub repository. So I will give now the word to Julien, which will tell us about the results on super resolution.
Thank you very much, Devis. Thank you very much, everyone, for being here today. So I want to focus here on the super resolution of optical sensors, and in particular, Sentinel-2, and bringing it closer to spot imagery. First, why do we care about super resolution? They are fantastic, very high resolution imagery products. Simply, they're extremely high cost. If we want, and when we wanted with Amnesty International, a single mosaic of Darfur, the cost with a generous 50% discount for NGOs was $4 million US. Obviously not the kind of money that actors like Amnesty International, like the Red Cross, like most for good social actors can afford. Arguably, this impedes the large-scale use of the fantastic tools that we have as an Earth observation community, both for these social good actors, but also for companies who do not necessarily have these deep pockets. And arguably, the existing data sets that are out here are somewhat too targeted. If you look at the fantastic resource that is SpaceNet 7, which is a widely used data set for machine learning training based on planet data, it is very focused on Western or global North urban areas, which does not work to detect informal settlement, refugee camps, destroyed villages in conflict zones. So this is what we try to set out here, is that we can use Sentinel-2 imagery, which is absolutely free, easily accessible thanks to Sentinel Hub, and covers the world with a revisit of 5 days. 10-meter resolution, spatial resolution, not necessarily enough for some of the use cases that would have the most impact. So that's what we're trying to do here by trading the temporal resolution, merging several subsequent revisits, and from that extracting subpixel information to get a higher spatial resolution and moving from the 10-meter to the more 3-meter type of interpolation and inference. Now, what we will be releasing and what you're going to see here is first the biggest data set that has been made for this kind of purpose, which covers 10,000 square kilometers of imagery, where we open sourced in Creative Commons spot imagery with the support, obviously, from ESA and Airbus on spot imagery paired with Sentinel-2 imagery. We will release train models to achieve what I'm going to show, and we release the code as an EOLearn Python plugin for both the inference, that you can use it as it is, use these train models, for the training in only 3 hours on a single GPU, because not everyone has gigantic GPU compute resources. So we focused on algorithms that can be trained easily on a budget. And of course, the code also to collect the data set if you so want to extend it with extra budget, or recreate it, or vary it in any way. I'll touch briefly on the algorithms. It's nothing revolutionary. It's things that we are proud of, obviously, but these are things that have been bouncing in the community for a while, including in the first versions of the work we did in 2019 on the Probavi data set and the Kelvin competition. If we look, the idea is very simple. You've got here the radiometric resolution of the different bands, and you can see that the Sentinel-2 bands have quite an overlap with the spot bands. So we are going to focus on the optical sensors here and try to map from the RGB and the infrared of Sentinel-2 and map that to the RGB of spot and the pan channel, so that we can target pan sharpened resolution. Pan sharpened has takes a lot of flack for scientific users, but for human rights monitors, for urbanists, it is massively used in their day-to-day to see the rate of change, to see the buildings, to see. Basically, this is the ideal to target for them. Algorithmic-wise, we're providing a baseline, which is the SRCNN that we adapted to handle not only multiple frames, but also multiple channels. So it is based on ResNet. You just concatenate all the different revisits and the different bands, convolve that to different channels, a set of 6 layers of ResNet, conv transpose to expand to 3 times the size, essentially giving you a factor 3 of zoom. That's a baseline. And we are also including our IResNet, which started in my previous team at Element AI, and that we have now extended to handle the multispectral setup of Sentinel-2 and Spot, basically based on the recursive fusion tree to be more data efficient and more compute efficient, but which is also based on ResNet and a series of merging steps until you get the transposition. What's interesting from an algorithmic point of view is to let the network learn what clouds to ignore, what wrong inputs and wrong revisits to ignore, entirely learned by the algorithms, and learning the implicit co-registration. There's a lot more in our article on HiResNet, which was made on single channel at the time, and that we now have on multispectral. But the most important, if we use Andrei Karpathy's theory of software 2.0, data is more important than code almost. And this is what we have to emphasize here. We have done our preliminary test with a aforementioned SpaceNet data set, but we really want to take it to the kind of use cases that can have the broad impact we want. I could focus on what I deeply care about, human rights, but actually we want it to be useful to more than that. So we went shopping, essentially. We went to UNHCR, the Haut Commissariat aux Réfugiés of the United Nations, in partnership with the Oregon State University, who kindly shared with us their data set of refugee camps locations across the world. We asked Amnesty International for locations of points of interest typically involved in their human rights campaigns. And we asked ISM Spotter, who kindly shared their locations on illegal mining in the wild. And this gives us these points of interest throughout the world, including in regions which you would rarely see, at least with such density, in existing data sets. We use about half our data sets for that, so 5,000 square kilometers. And then we went to think, okay, how do we sample the rest of the world so as to have maximum usability by a maximum range of applications? Well, again, we turn to the European Space Agency and the extensive products that exist there. In particular, there is this CCI-LC land cover atlas, which has this deep hierarchical classification of the world by land cover. Is it perfect? No, it's at a fixed date. It has, many limitations like everything we do. But it is there. It is highly thought through, and so let's reuse that. So we have a mapping of the CCI-LC maps to the classes used for, especially for climate change configuration by the International Panel of Climate Change. As we can see, there's this broad classification into agriculture, forest, grassland, wetland, settlement, which is just one class here for urban. We'll come back to that in a minute. And a lot of lichens and moss, shrublands, bare areas, and waters, and including actually a seventh one not pictured here, which is just not classified, which is mostly ice shelves, which are of interest to us. So we use a stratified sampling to make sure that we cover everything. But that still gives way too much weight to lichens and mosses. And much as I'm sure there is a high community studying lichens and moss in the world, their proportion in the population of people interested is somewhat inferior to the proportion of space in the globe that they represent. So we renormalize by using the qubit root. We use an important sampling algorithm so as to reweight the different classes so that we can still have an unbiased estimate and unbiased representation of the world while enriching the classes that are potentially more useful. So the highly represented class gets somewhat less represented, and the poorly represented classes, such as urban, get more represented. And actually for urban, because so much of the human activity and the human interest is around the constructed areas, and because the time resolution of super resolved image lends itself well to static structures like buildings, we super sample the urban class in the following way. We add, obviously, I think around 25% of the data set to be urban, but then we sub-stratify it according to the global human settlement layer and its S-mod product, which allows us to sample uniformly across these different levels of density, which are of a specific interest to urbanists wanting to see the extension of the urban sprawl over the years. So with that, with this stratified and importantly weighted areas, we obtain this point of interest, which for all types of land covers, we even have some on the ice shelves, as you can see, stratified, so with a fair representation of every type, and with enrichment in urban areas. And eventually, when you put all of them together, here are all the POIs that we end up having. So what do we do with this data set? I mean, concretely, this gives us 10,000 square kilometers. To maximize the diversity, we have focused in the smallest tiles that can be orders, a minimal contiguous order side, so as to have the maximum number of tiles and views of the world. So each tile is 2.5 square kilometers, that's roughly 1.5 kilometers to the side, with here the different, I won't read the slide in detail, but essentially half of it on the land cover and half of it on the more humanitarian and underserved areas of interest. Now, what does it give us? Well, here is a view of Vienna, and that is the palace in Vienna, where what we will see here is a quick view of zooming in on Vienna in Sentinel-2. Here we see the different layers, 4 revisits that we take and that we merged. And we merge these 4 Sentinel-2 revisits to obtain this super resolved view here. So if we go back and forth a few times, we see obviously much more details interpolated through these only 4 revisits, which a revisit every 5 days leads to about 20 days of temporal resolution for, again, much more details. If I were to zoom in on a wider range of terrain in the next slides, and showing again the variety of revisits that we can have. So here's an entire scene in Sentinel-2 with the different low resolution revisits. As you can see, many of them were cloudy or missing. If you look in this zone, we have 7 revisits, 2 of which are absolutely not usable. And the algorithm learned to ignore them and just merge the remaining 5 to the level that we are seeing here in this slide, where we can actually see much more the detail of the building and the structure there compared to the low resolution that we have in a Sentinel-2 10 meter per pixel imagery. This is roughly a zoom to 3 meter level. And we'll zoom out in a second to other parts of this large scene to show equally different aspects. There's a lot of discussion to be had about the protocols for evaluation and the presence of artifacts, and there's a very lively debate. So I know there's a seance organized at the Living Sphere Symposium, Living Planet Symposium later in May to discuss this. But essentially here, again, you see one revisit that is absolutely useless. We show slices of every possible Sentinel-2 revisit on this area, just in this view, to give a taste for how varied they can be, and then the merged results super resolved, where again you can see much more the structure under concern, the different dome-like shapes, etc., and the vegetation around it. The reason we merge multiple revisits rather than doing a single revisit is precisely to try and limit the chances of hallucinatory artifacts created by just imagining what is in the pixels. We exploit the sub-pixel differences. As you can see here, we have these different views, again, one very cloudy and one just plain missing of this area with a lot of small path, that when we actually merge them, we can actually detail and find the little path and the different buildings aside this path in this foresty area. Now, yeah, I think that's the last one that we zoom on. And again, these different revisits for each of these stripes, we do have the full Sentinel-2 imagery. We're only showing one stripe as a quick way to visualize the difference of quality. Again, we did not teach the algorithms to ignore the clouds. That's the power of machine learning, essentially, to learn to ignore those. Is it perfect? Not yet. That's why we're still working on it before releasing. So concretely, what we are releasing, or will be in the coming few weeks, is the data set, first and foremost, which has spot and sentinel matched imagery for 10,000 square kilometers, again with a maximum amount of diversity in the tiles, with the smallest possible tiles. These are stratified to have an extensive covers of human rights interest, urban times, and generic land cover. We release also the code to regenerate this data set if you so want, and if you have the budget to add more spot imagery, or if you want to add more the different sampling strategy among the different classes, or if you want to extend it with playouts data or any other source. Importantly, this data set, while we use it for super resolution, can have for users way beyond. When we look at the Tile2Vec work, for example, for semantic embeddings of satellite imagery, as done in the Herman's lab in Stanford, this data set can be used for that, and arguably has fewer biases than the data set that currently exists. We also release the trained models so that you can immediately get to play with them or fine-tune to your own needs. And of course, we release open source Python code in the form of a plugin for EOLearn that allows both for easy inference. Inference is pretty instant because we have kept our model small at any location of your choosing, not just obviously the location in the data set. That would be somewhat limited. And we also provide the code for retraining on any new data set. And we've made sure for reproducibility, again, that this can be trained in under 3 hours on a single V100 GPU. So we have not optimized for getting the biggest model we can ever have. We have optimized for what can be reasonably expected to use by any researcher or any even data scientist in an interested organization. This is going to be released around May, by the time where we submit it to a machine learning conference. And if you're interested in being notified as soon as it's released, here is my email, or you can follow me on Twitter. Thank you very much for your attention. Thanks ESA and the consortium to work, and special thanks to Ivan Orstolich for his amazing work on this. Over to you, Benjamin.
Yeah, thank you very much. Yeah, my name is Benjamin Bischke. I'm from Vision Impulse, and I have the pleasure to present you today our work on a large-scale forest mapping on a European scale using deep learning. So before we go into the methodological details and the applications, let me briefly go over the motivation and the aim for this work here. So as we already said a couple of times, this work mainly focuses on forest monitoring, and this is because forests are very important for many reasons. So on the one hand side, they provide from an economical point of view, they provide important assets, resources with a high value for nature. They are vital to preserve, for instance, biodiversity. And also, if we think about climate change, that is becoming more and more important. Forests also are an important sink for storing carbon dioxide. While at the same time, if you look at that we see an increase of extreme weathers, of disaster events that are threatening forests, there is, especially in the recent years, an importance and a necessity to provide and continuously more forest monitoring with a lot of details about the status of current forests. And this can be also seen in the Sustainable Development Goals, this importance. So if you look, for instance, at the goal 15, life on land, or also at 13, climate actions, you can see that forest and in particularly forest monitoring is a really important topic also for the United Nations. So for instance, there are sub-goals such as ending deforestation, providing a more sustainable forest management, restoring degraded land, but also protecting biodiversity and natural habits that are directly linked to forests. And of course, also, if we want to evaluate the progress on these Sustainable Development Goals, it is also very important to continuously monitoring KPIs of forests to get information about the status of current forests. And this is the goal of this project here. So if we look at what is currently done, we can see that many forest maps are often not up to date. So on the left-hand side, you see an image from Sentinel. So this is a Sentinel-2 image for 2020. And on the right-hand side, you see the current dominant leaf type layer that is available. You can see that there are many outdated annotations. So for instance, a lot of this forest area that is still marked in this map is already been cleared. On the other hand side, we see that also new areas have been grown up, which are also not really mapped here. And if we see this over a large area, so over Europe, you will see later on more examples. We can spot actually a lot of different examples in these cases where we do not have any more up-to-date information. And not having such information, so outdated information, and on the other hand side, also not being able to having such information in real time. So often generating these maps takes a couple of years to produce it. So the last available dominant leaf type layer, for instance, is from 2018, which is now already 4 years old. There is a race of methodology and pipelines in order to extract this information at real time on a large scale. So this is also the aim of this project. On the one hand side, using Earth observation data, mainly information from ESA Sentinel-2 satellites, exploiting the multi-temporal aspects and the high cadency that the Sentinels provide. And on the other hand side, also using artificial intelligence and in particular deep neural networks in order to leverage this multi-temporal information and overcoming this problem of having out-of-date information. So let me go into the details of what we did with respect to the dataset models, a few experiments. We did more experiments, so here you see just the highlights. First of all, this work is heavily based on Earth observation data. So we use, as I already said, Sentinel-2 imagery, atmospherically corrected imagery. We took the complete time series for 2018 and 2020 for the European surface, the EA39 surface that you can see on the right-hand side of this picture, which is roughly about 140 terabyte of data, of raw data. And for this raw data, we derived several machine learning data sets where we could use it then for training our machine learning models, our deep learning models. And what we did here for generating such data sets, we first split the raw data into smaller patches so that we can work with. Here we used a patch size of 128, which is rather small, but on the other hand side, we also have the complete time series, which is very dense. So this is just a constraint because of the memory of current GPUs. We sampled from this surface that you see on the right-hand side proportionally to the country size so that we do not have any oversampling for certain countries. And in this work here, we mainly focused on classifying 3 classes. So the broadleafed forest class, coniferous forests, and no forest or background in this case. And we mainly focused here on the available annotations from dominant leaf type. So this is a layer which is not really a gold standard data set, a silver standard data set. And additionally, we complemented it also with own annotations for particular areas from our side. Now, having such a data set now, you can see here, for instance, the Sentinel-2 imagery. So this is just an overview where we used monthly images. So this was for one particular model, and you can see also the different variations also in these images. So from the model perspective, what we did here and what I want to present today are 2 baseline models from the field of deep learning. The first is a UNet. So UNet is a typical, I would say, state-of-the-art network from deep learning that have been used in many approaches. We extended here the model towards a multi-temporal, to cope with multi-temporal data by stacking here the different temporal dimensions together. Here we used the fixed size of temporal information and passed this to the network. And the output is, of course, here in this case, a segmentation mask for the different forest types. The UNet here is a very state-of-the-art model with the encoder-decoder, and here we use ResNet50 as a feature extractor in the encoder. Second model, which is more towards the multi-temporal aspect, is a convolution LSTM. So this is typically originally coming from signal processing. So there have been some modifications. For instance, in this LSTM, you see here that there are convolutions used, and this allows us to basically apply also images to this LSTM model. And what we can do now is, with the LSTM model, learn very well the temporal dependencies of these images. And at every time step, we can basically predict already a forest map. So this has the great advantage that the time series is not restricted to a certain length, so we can be very flexible with it. And on the other hand side, at every time step, we can get a new segmentation mask out of it. With these 2 networks, we also provided or we used a couple of validation data sets for generating such maps at a large scale. So one data set that we got from a research project that we did together with TU Berlin, for instance, is from the TreeSet.ai data set. And here we got access to National Forest Inventory over Germany. We used here a data set where the good part of this data set is that it's high quality annotations from experts where they really annotated individual tree species. We have annotations from the same year that we are also generating the map for 2020, and overall more than 5,000 individual tree stand observations or point data that you see on the right side. Here for the first evaluations to get some quantitative results, this is based on the validation data that I just mentioned, both models. And we have 2 different cases that we evaluate. So a binary case, forest versus background, and also the 3 different classes. Here are the results. And what you can already see here is that the convolutional LSTM achieves here the best results. So for the binary case, around 59%, and for the forest types with a 3-class model, 92%. We additionally also used another validation data set that is a bit more on a larger scale. So this is the Lucas data set that is provided by the European Union from Eurostat. This data set has more point data annotation, so it's also not a segmentation mask, but based on individual points. However, it allows us to have a larger spatial coverage, mostly over the complete European surface. The only drawback on this side is that it's not completely up to date. So it's from the year 2018, while we are predicting on 2020. So there is a bit of a shift in this time, But on the other hand side, we also did not see that many changes for the 2 years. And if we also evaluate the approaches with this, on this data set, what we can see over here is, so this is just based on the convolutional LSTM and the year 2020. So we can see that we achieve very similar results compared to the data set from the National Forest Inventory, roughly about 59%, and for the forest types with the 3 classes, 92. And we also compared the dominant leaf type product that is provided for the year 2018. And here we see that we are quite well on par. So there are a few changes which we don't have, but on the other hand side, the comparison is not completely fair also, since we are using a more up-to-date data set basically, or input data. But overall, we are very similar to these results. Now, the big question is, now that we have such models, what can be done with it? And here I have a couple of examples to showcase this a bit more. So here you see on the right-hand side, on the left side, sorry, you see the image from Google Maps. So this is an aerial image. On the right-hand side, you see a Sentinel-2 imagery. And this was the example from the motivation. So you see that clearly that there is a clearing of forest that is not here anymore. And if we compare the existing maps, we can directly see here, so this is the existing dominant leaf type layer, that this is not up to date anymore. And this is here on the right-hand side, you see our recent prediction, and here you can clearly see that this area here where we see the forest clearings disappeared, while on the other hand side here in the northern region, that is not in this dominant leaf type layer, we are able to also segment this and provide up-to-date information. And we can do this now at every new incoming layer for Sentinel-2 scene. So as soon as every few days, as we get a new satellite image, we apply this model and can update the forest map here. Another example showing this on a broader scale, here you see a wildfire event for 2020. That's near the German-Netherlands border. It was mapped from the Copernicus Emergency Service. And again, if we compare the existing layers of information here against the new forest map, we can directly see that the areas here are identified as burnt areas and not as forest anymore. So we can directly update here as well the information. There are a few more examples. For instance, here over Germany, we see clearly here in the Sentinel-2 image that some parts here have been cleared or cut down. Some are because of storm events. And again, if we look here and compare the different products, we see again a lot of changes that are correctly mapped. Yeah, this is a bit more on a higher scale to compare the two. Here, this is another forest clearing in Slovenia. And if you go over the map, we see a lot of these cases where we see changes or information that is not up to date anymore. Here, for instance, in Poland, so this is some commercial area here where you can directly see there are a few, for instance, here in these tribes, there are a few cases from the past, but we see also that a lot of areas here are new identified. And with this, we can directly quantify the amount of deforestation, the amount of forest that has been lost, but on the other hand side, also forest gains. Yeah, this is a more example view. So to sum up this project and the outcome of this project, here's an overview. So this is twofold. On the one hand side, we have here, we created a pan-European forest map for the year 2020. So this is more up to date than the existing one. We have here a web application where you can go into it. I will go more in a second. And the other big outcome of this project is here a IPython notebook where you can basically do very similar on your own. So we have here an example on how to acquire satellite imagery using it from Sentinel Hub, getting the time series, running the different models that we provide. So you get a lightweight model from our site, where you can also extract binary forest maps, the different dominant leaf type layers as seen in here. So let me go first to the forest map. We have a demonstrator available, which is available here at this link. You can see here on the right-hand side, there's our layer, which is included, the recent dominant leaf type layer, and for background information, we also included a couple of related projects, such as the S2 Cloudless product, basically the cloud-free Sentinel-2 layer, and from ESA World Cover as well, a segmentation was to compare the different maps and project results. If you are interested into getting updates and real-time alerts about forest changes, forest degradation, forest deforestation alerts, we also are providing in the next couple of days a forest monitor. So if you are interested, feel free also to sign up here for this monitoring service. And last but not least, now also to the IPython notebook. As I said, there is a complete reference to follow from getting the imagery to the results and applying it on a larger scale. The IPython notebook will be available very soonish under this link, and also Sentinel Hub to set up a trial account. Just follow this link here. So this concludes my talk, and now I think we can go over to Devis.
Thank you. I will start describing then the Hector, so our hierarchical object detection tool. So what's the motivation? So similar to what both Julien and sort of Benjamin mentioned, in particular in this case for detection on man-made objects, usually this task requires very high spatial resolution, so typically lower than half a meter, and typically aerial imagery is used, or again very high resolution satellite imagery. This also means that since actually this imagery is available at a very high cost, so it's commercial imagery, it means that this kind of task, especially to be run on large scale, are limited to very few players which have basically the resources both to access the data and the resources to process it. So what Hector tries to basically do is to increase the access to everyone sort of in the community so that they can perform this task at large scale. So the main idea behind this is that actually what we are interested in, so these man-made objects that we want to detect. In our case, we will focus on buildings, but the same could apply to different like bridges, cars, airplanes, which are typically the target of object detection tasks, are very sparse, which means that they cover a very small percentage of the area of interest that we are interested in. So the idea is very simple. The idea is to perform a hierarchical detection using multiple source and multi-resolution imagery. So first, we start doing the detection at a medium, high resolution, using a medium to high resolution imagery from say 5 to 15 meter spatial resolution, which helps us give an approximate localization of the target objects. Once we have these localizations, we will focus only on these areas, and we would request and process and run detection with a higher resolution imagery, typically from 1 to 5 meters, where we can detect then large to medium objects. And this detection will also allow us to find areas where smaller objects are present, where we would need higher resolution imagery. So then on these areas only, then we can sort of then drill down and request even higher sort of resolution imagery, typically lower than 1 meter. And this will allow us to detect the smaller objects. So we will show you then how sort of we build a prototype. And while sort of Hector is meant to be general, so you can use different commercial satellite imagery. So we build the prototype using ESA Sentinel-2 imagery, using the 4 bands at 10 meter ground sampling distance, Airbus spot imagery, pan-sharpened, so the blue, green, red, and near-infrared band pan-sharpened at 1.5 meter pixel size, and Airbus Pleiades imagery pan-sharpened at 0.5 meter. So here is an example of the same area imaged by Sentinel-2, Spot, and Pleiades. And with Sentinel Hub, you can access, you can order and access each of these and treat basically each data source as a data collection, so abstract the way you can access the imagery. So we evaluated the method over 2 areas. So first, we built the models using data in Azerbaijan, which is roughly 86,000 square kilometers. And then we tried to evaluate how these models generalize to different areas. So then we fine-tuned these models to Dakar in Senegal over an area of around 500 square kilometers. As mentioned, sort of this hierarchical approach can be sort of disconnected to the kind of task, but we focused on object detection, meaning that our model directly estimates bounding boxes, and in the specific, it estimates oriented bounding boxes. So we focus on this because we've seen that they provide a good approximation of the building footprints. As you can see here on the right-hand side, so on the top image shows in yellow the outlines of the building footprints, while the middle image shows the approximation using axis-aligned bounding boxes, while at the bottom we have oriented bounding boxes. So you can see, as shown in this histogram, that actually the oriented bounding boxes approximate better the original footprint. So this histogram shows the ratio of the area of the oriented bounding boxes over the original building footprint. And you can see that for the majority of buildings, actually, we have almost an overlap of 1, meaning that the oriented bounding boxes is almost completely overlaps, perfectly overlaps with the building footprint. Also, it reduces the post-processing. Often we are interested in sort of a polygon that describes approximates the building, and we get this directly from the model, so we don't need to do any post-processing as is required if we did semantic segmentation. And similarly, so as opposite to semantic segmentation where we predict on the pixel, which then we need somehow to post-process, object detection is less sensitive to different pixel sizes of the different imagery, since we estimate directly the locations, the 4 corners of the bounding boxes. We use an existing model, the single stage rotation decoupled detector, which was recently proposed in the literature, which uses pyramidal feature extraction and is based on ResNet architecture. So we used a ResNet 34 feature extractor, which then the features are combined in a pyramidal way to estimate the oriented bounding boxes. So we separated for the training the 2 models, one for Sentinel and then an analysis separate for Spot and Pleiades. For Sentinel, we consider imaging data for the entire country, and we also had sort of, even though outdated, information about footprints for the entire country. And in this case, so we treat this separately from Spot and Pleiades imagery, since in Sentinel-2 we can't really detect or resolve single buildings. So the oriented bounding box here denotes more a built-up area rather than a single building. And then we build this SSRD model using cross-validation. For Spot Pleiades, we run different experiments, both training models separately for the 2 data sources and together. And we've seen that actually with a single model, we can achieve good estimates for both the image modalities. So we train a single model and we use a very small percentage of data where we need the higher resolution imagery, both Spot and Pleiades. And we did this with a total area, so we had small AOIs spanning the entire country, but of total area of around 9 square kilometers. so very small percentage of the total area of the country. And in these areas, we manually validated the labels, because this is very important naturally to have very accurate labels. So in total, there were around 66,000, so not that many. And also in this case, we train using cross-validation, and by training them together, sort of the model learns multiple scales, features on multiple scales that helps the detection on different data sources. Once we have our models trained, we can do inference. So given an AOI, what we do, so we split it, in this case, into a grid with cell size around 10 kilometers. And for each cell, we get the Sentinel-2 imagery and run the detection. Once we have the detection, we merge these polygons to obtain sort of a multi-polygon that describes built-up areas, as in this case. Once we have this, then we further split this polygon into a grid with cell size around 700 meters. And we will use these to order the higher resolution imagery, in this case, the spot imagery. And once we have the spot imagery, we run the detection. We will get estimates of the buildings. And what we can do, then we further split this area into smaller cells, in this case size 80 meters. And we compute an index that tells us basically how confident is the model in those areas. And this measure is sort of proportional to the density of the buildings and the confidence in prediction of the models. And this allows us to find, like in this case, areas of very densely populated areas with small buildings, which are shown in dark red. And these then are the areas where we're gonna request higher resolution imagery and run the prediction. So in this case, for those areas, we will request Pleiades imagery, run the detection, and then finally we merge the spot and the Pleiades predictions. So all these numbers are customizable. So we made these as generalizable as possible to different sort of application or requirements. So these are some visual results of the prediction using Sentinel-2. So you see the model is quite robust to different scenarios, to different land covers, so agriculture or more desert. So even if we have areas with quite a bit of bare soil, the model is quite confident and uses sort of textural features to tell apart built-up from non-built-up areas. And these are some results of the detection using spot. So you can see there's some false positive, since actually the model has mostly seen buildings and not, in this case, the sea or the agricultural fields. So there's still some room for improvement, of course. But we can see that it's able to estimate sort of buildings both of larger and sort of smaller scale. And these are some results for Pleiades. So you can see the Pleiades model is, of course, sort of more accurate, in particular in areas where you have a lot of small buildings very clustered together. And this is the final result. So once we merge these two predictions, we have for very dense areas, we use the Pleiades detections in green, and for the rest, we use the spot detections, which you can see here shown on Pleiades imagery. They are quite accurate. So this is the quantitative results. So then we evaluated sort of what is the trade-off between then the cost saving and the accuracy. And by doing this process and using Sentinel-2 to basically request a lower amount of data. So for Azerbaijan, we were able to request only 37% of the area of the total country, with only a 0.6% sort of loss of buildings, which results basically in more false negatives. And this just slightly affects the score, which here is computed as mean average precision, but already with the saving factor of 2.6. So here shows if we run detection using Pleiades only, at the whole country, we get a mean average precision of 0.45. If we add Sentinel-2, we lose a little bit, but we gain already a 2.6 in cost. And if we do this on spot, which is cheaper than Pleiades, then of course sort of our accuracy decreases. And putting everything together, Sentinel, Spot, and Pleiades, we sort of move between this column, so going from Spot to Pleiades depending on the threshold on our drill down index. But again, we can achieve very large cost savings, so 20 times with sort of accuracies which are closer to using the full-scale, very high resolution imagery. So then once we had this, we tried to transfer the models that we train on a new area, in this case in Dakar. So we use Sentinel-2 without any fine-tuning, so directly. And we could get sort of good estimates, even though the model was less confident, as you can see. So in blue is the confidence of the model in Dakar, and in salmon is the confidence for Azerbaijan, where it was trained on. And for Spot Pleiades, we fine-tune on a subset of buildings, around 7,000, again, manually validated. And you can see here some example. Is sort of the drill down index shows that the majority actually of areas in Dakar are very densely sort of populated by small buildings, as you can see in the example below. And even though we trained sort of fine-tune a very small subset of labels, we get sort of estimates which are comparable to sort of state of the art. In this case, it's just an example showing the open buildings dataset released by Google. So what we open source, again, QueryPlanet is about open sourcing and allow you to repeat and build on what we've done. So we're open sourcing the models and the labels for Dakar. So they're published on the QueryPlanet open bucket under a Creative CC non-commercial license. We have released the code which allows you to train and run inference, and is published on GitHub on Sentinel Hub Yector repository under MIT license. And also we have separately sort of in the year-learn examples Yector directory notebook to run inference. So you have an end-to-end example where you will be able to basically run through the entire steps of inference on your laptop, and we will do this in the next webinar. So this is it from my hand. I think I will give the word now to Sabina, which will lead Q&A session.
Thank you, Devis. First of all, thanks to all presenters for your excellent presentations. So let us proceed with your questions, and let's continue with the questions already asked in the chat. The first one during Julian's presentation was from Fernando. He was asking if Julien can elaborate a bit more about data pre-processing for training, about date synchronization between Sentinel-2 and Spot, and pointing angles, etc., and spatial registration. So I give the word to Julien.
Thank you. It's a great question, and I could actually spend an hour going and waxing lyricals about the details, because I love geeking out about that. To avoid inflicting that on everyone, with the data set, we're also releasing a technical report that actually has all these details. The short story is data synchronization by looking at the catalog and finding the intersections, and no explicit registration. We want the network to learn it, but all the details about the classes and how we do exactly that will be in the tech report.
We got one more question from Jeremy. He was asking if this is also intended to perform super resolution on a given Sentinel-2 band.
The way multi-frame super resolution work, at least with this machine learning approach, is that we can super resolve to the target, the bands included in the target training data. So in this case, we are targeting the bands from Spot, the RGB and the panchromatic. There is an implicit spectral convolution and deconvolution involved, and that is learned. So if you want to do target one band, you would need to have the NDVI and retrain on that, and you need to have the NDVI on high-res. Alternatively, you can combine the, well, yeah, no, you're stuck to actually what you have in your high-res data and combinations thereof. If you can manage to get some higher resolution NDVI layers, then we can train for that, yes, and the code is included for that.
Jeremy's second question was applying that if that would mean network architecture would not be working without adaptation for training from one band images such as NDVI, for example.
So if you try to train from one band to another target, yes, you can retrain, which is why we provide the code for retraining and why we focused on an architecture that is lightweight, so it can be retrained. I mean, we trained it in even an hour and a half for the version on an external GPU connected to a laptop. So these adaptations are definitely there, which is why we release the code for that to be allowed. That the whole point of EOLearn and QueryPlanet is to have as many people as possible adapting to their needs. I'll be very happy to have a separate conversation on how to do that. We have a workshop next week, sorry, April 7th, the second part of this webinar that shows hands-on demonstration of using the Jupyter Notebook. So I encourage you to join there too.
Sandy was asking, do you discard the whole tile for image tiles that are unusable, covered by clouds, or is there a smart filtration to maximize enhanced visits?
Being a machine learner obsessed with end-to-end learning, I try to avoid having a hard discard. We can, there is a way to filter that if you want, but ideally, and that's what we did, you want your algorithm to learn to recognize stuff that it should ignore and extract signal from the part of the images that are not covered by cloud. So no, we do not have an explicit filtering. It's there as an option because that's the kind of things you want to benchmark and compare, but the architecture does not require it.
Thank you, Julien. And we can continue with the next question, which was set during Benjamin's presentation. So the question is applying to you, Benjamin. What's the input to your LSTM convolution as an annual stack? And if so, how about the labels? What if an area gets clear mid-year?
Yeah, so that's a great question. We did actually a couple of experiments on this side on using, for instance, monthly mosaics for the complete year, using every time point itself over the complete year. And what we figured out is, on the one hand side, using the complete time series gave us the very best results. However, if we just switch to the typical vegetation period, so omitting January, December, February, typically the information where it's covered mostly by snow in a lot of areas, we do not drop in the performance metrics just by 1 to 2 percentage points on the intersection over union metric. So in general, the LSTM model can be applied to different time series length, basically. And we've also figured out that the mid-year changes are actually not that frequent, and the training and the model are quite robust to cope with this kind of noise, especially since we have such a large data set.
Thank you, Benjamin. We have a minute or two more to take another question or two. So maybe, Devis, this one for you. Is there any method to calculate NDVI from Sentinel-1 data?
So regarding this question, so as you probably know, the SAR imagery is very different sort of from optical, right? So you won't find an exact sort of band with the same information. However, you can find some combinations that can sort of convey a similar information as the vegetation index. So for instance, if you checked the on Sentinel Hub, the custom scripts, you will find a radar vegetation index for Sentinel-1 SAR data, which will probably provide you this index, which can sort of provide similar information to the vegetation index, if this was your question. We've seen also there are sort of machine learning applications that try to estimate sort of vegetation indices from input SAR bands. But then, of course, they're sort of a bit more complex, and they try to do this non-linear mapping between the two data sources.
Thank you, Devis. And I believe we have time just for one more question from Richard. He was asking Benjamin, as far as he remembers, the forest detection was better for the old forest map from 2018 compared to the more detailed map from 2020. So do you have an explanation for the good performance of even or outdated data with the detection?
Yeah, that's a great question. For this experiment, which I showed, the reference data was from 2018, and we compared it to the dominant leaf type layer also from 2018. So they have been both from the same year, while the map that we generated and that is in this demonstrator is from 2020. So there are, of course, a couple of different changes. And as you saw, especially a lot of deforestation cases that are now classified as false positive, which is not the case for many cases. So this has certainly influenced that it's not the complete year that is also used for the reference data.
At this point, I would also like to invite you to see more information about related to our webinar on the stated links which you see on the screen. First of all, you can apply for a trial account for Sentinel Hub, which is for 30 days at the first link, or you can also apply for a grant from ESA sponsored accounts, which are for pre-commercial exploitation phase, or you can even use the opportunity to get free access to commercial data. If you have more questions, I would invite you to use our forum, check EOLearn links and EOLearn examples. And of course, I would also like to invite you to our next webinar. This will be the second QueryPlanet webinar, and it will be organized as a hands-on tutorial on how to set up and execute the use cases which are developed within the project. It will be held in 2 weeks, so on April 7th, and we hope to see you then. Thank you all for attending, and we wish you a nice rest of the day.